This week, we moved from linear models to neural models. I call this neural network, but it will be mainly multi-layer perceptron and a neural language model. So we'll first give a review of how you move on from one layer to multiple layers. I'll show you a perspective of multi-layer perceptron from NLP aspect. And then we will discuss neural n-gram language models and how to represent words using dense vectors. First, let's take a look at multi-layer perceptron. Okay, so this is a review of the neuron we discussed in week 5. So you have an input representation, which is a vector, and you use a model parameter vector, which is of the same size of the input vector. You do the dot product, and then an activation function to calculate an output. Okay. Now, let's assume that we're doing binary classification. So the output is either +1 or -1. Okay, we're going to move from here to a multi-layer version of this perceptron. Okay, so let's first build up the second layer artificially. Okay, so let's assume that we have a lot of different outputs. Maybe the first one is the sentiment of the input. Well, we're assuming that the input is a document. And maybe we assume that the second and third one are about whether the document is a sport news article or a political news article, okay, etc. So until we build n of them, so we build n output nodes. So each is a binary number. We put them together. And then if we take this output, okay, as a vector, and we stack another neuron on it, we got a 2-layer perceptron, okay? So the output layer might be something more abstract than what we discussed in the previous slide, okay? For example, maybe the output, as I noted, O, okay, means that something John likes, okay? It is a combination of features we have from the second layer. Maybe John likes political news with negative sentiment, etc. Okay, so it's a composition of the outputs in the second layer. And no matter what, so this is a 2-layer perceptron structure. Okay, so there is a layer in the middle, okay, which creates a set of intermediate features. We will see later, okay, or as we will review later, okay, this second layer can be trained automatically. We don't have to manually specify what each neuron in the second layer means, okay? But we can train the neural network to calculate the second layer nodes if we have annotated data from the first layer to the third layer, okay? All right, in other words, the neural network might learn some very abstract features in the middle if we just show it a lot of things John likes or John doesn't like, okay? And of course, we can extend this 2-layer perceptron to 3 layers. And in this case, the hidden layers, or the layers in the middle, are even more abstract. Okay. And why do we call them hidden layers? Because they are learned automatically, and they're in between the input and output. Okay, they're inside the neural network. So we call them hidden layers. So both 2-layer perceptrons and 3-layer perceptrons are called multi-layer perceptrons, or MLP. Okay, both of them compute nonlinear functions. Do you remember in week 5 we used to say no matter what kind of nonlinear activation functions you use, your neuron is a linear one. Okay, it can only separate linearly separable instance spaces. But multi-layer perceptrons are nonlinear. And they can do that because they stack multiple nonlinear activation functions together. So they can learn these functions. Okay, so since we're talking about activation functions, we don't know too many of them, right? We know the identity function, which is for SVM and perceptron. And we know the sigmoid and softmax functions, which are for log linear models, right? So here, I show you 4 more of them, okay? So one is called ReLU, rectified linear unit. What does it mean? Okay, it's a very simple nonlinear activation function. It takes the value of x if x is greater than 0, and takes the value 0 if x is smaller or equal to 0. So this is a hinge function, right? Just a hinge shape. It's nonlinear, of course, because it has 2 subsections. However, it's simple. There used to be a stage where people find that even calculating exponential functions are too heavy, okay, for a fast neural network. So people selected ReLU for achieving a fast nonlinear functionality. And it turns out that ReLU works quite well also in some of the neural networks, such as transformer. There's another nonlinear activation function called tan(h). Similar to sigmoid, it's applied to neurons one by one, okay, without linking different neurons together. But different from sigmoid, tan(h) takes a range, okay, -1 to 1, -1 to +1, okay. So it's another exponential function. So the function, I will not repeat it, okay. So there are also 2 other functions which I leave it to you to read for more information, okay. Now, since we are working with multi-layer perceptrons or deep neural networks, we need to change our notations a little bit. We used to have the theta phi notation for linear models, where the input is a phi, okay, and the model parameter is a theta. So if you look at our 2-layer perceptron, you find, okay, from the first layer to the second layer, I have a lot of thetas, right? So theta 1 for mapping x to y1, theta 2 for mapping x to y2, until theta m. Suppose that we have m nodes in the second layer. So is there a convenient way for us to denote it? Denote the whole linkage between the first layer to the second layer. All right, it turns out that if we treat each of the theta as a column vector, okay? This is a row vector, this is a column vector, okay? So if we treat every theta as a column vector, and then we we just juxtapose them, okay? Theta 1, theta 2, theta 3, right? Okay. Imagine that. That will be how many rows? The number of features you have, right? The number of rows we have. How many columns? M columns, right? So that will be a dimension feature. Let's say we have D features. So D by M matrix, okay? We call that WY. In the neural part, okay, we use bold fonts for denoting matrices and vectors. And we use capital letters for matrices and lower letters for vectors, okay? And what is more, given this WY, okay, we can have a very simple equation. Y is equal to WY times X for expressing the mapping between X and Y. Okay? How come? So if we treat this X as a column vector, right, and we multiply this matrix on the left, okay, we will end up with a column vector of M dimensions. That is Y. All right. So the second thing you find that is that in the neural notation, every vector is a column vector. Okay? Where is the activation? So we just need to put this activation function, okay, out of this W and X. What does it mean? So if it is a point-wise activation function, we apply it element by element in the result, all right? If it's a vector-wise activation function, such as softmax, we just apply that over the whole thing. Okay, so this is the notation. As long as you remember, so in this Y, every column is a mapping between X and Y. That's fine. So in this WY, okay? So when we have 3 layers, okay, we don't want to spend the time naming each hidden layer. So a common practice is to just name every hidden layer as H. But we use subscripts to denote the hidden layer number. H1 for the first one, H2 for the second one. So from X to H1 to H2 and to O, right? Okay. So H1 and H2 are highly similar. This O is V transpose times H2 rather than a W times H2. Why is that? It's because this O is a scalar. We only need a parameter vector. Okay, originally we had theta, but now we call it V. Why do we transpose it? Because this is the dot product. Okay, row, column. When we multiply them together, it's a scalar. Okay. So that's all easy to understand. How about multi-class classification? We showed that on week 5, right? So there are 2 ways we can do multi-class classification. One way is we say, okay, we have an input-output representation. We map that to a number, okay? So on the slide and on the whiteboard, okay, blackboard, I showed how you can turn input-output representation into an input-based representation with many different H, okay, to output representation. So for multi-class classification in MLP, the last layer, okay, is similar to the output layer or the only layer in a multi-class classification SVM or multi-class log linear models. So the input is here, okay, H. It used to be phi, right? And then I have one layer to map this H to O, okay? And I can simply denote that as O is equal to WO times H, okay? So where each column in this WO is a theta for the corresponding class label C, right? Okay? So O is equal to W times H. So O is a vector that stores the score of every class label. So the vector has the size of the class label set size, right? And then if we apply a softmax over O, we got a distribution just like a log linear model, right? Okay. So this is for multi-class. So if you compare this one, right, binary classification and this one, multi-class classification, you find that the input to hidden are exactly the same, right? Input to hidden mapping, the same. It's just that the hidden to output mapping. So the binary case computes only one output, right? 0, 1. Multi-class case computes a lot of outputs. Each one is the score of a class label. Okay? So that's the difference. All right. So this is to compare MLP with binary classification and multi-class classification. Now let's compare MLP and single layer neuron. Okay, so this is for the binary classification case. On the left is the neuron we have on week 5. On the right are the 2-layer perceptrons and 3-layer perceptrons. And you can find that actually the only difference is that we have more hidden layers than before, right? So if you remove all the hidden layers, if you only look at the last layer, okay, the output layer, multi-layer perceptron is the same as a neuron. Okay? So this is for the multi-class classification case. If you compare a single layer neuron and a 2-layer perceptron, you will see that the output layers are the same. It's only that we added a hidden layer for the multi-layer case. All right? So, in other words, so the neuron maps a input representation phi directly to an output vector. But multi-layer perceptron first calculates sort of a set of hidden representations, right? And then it maps the hidden representation to the output, not the input representation directly. So, what is the purpose of this hidden representation? The abstract feature we learn. Okay, I mentioned to you earlier that they make the multi-layer perceptron non-linear, right? So they actually increase the representation power. I use this picture to show you. Now suppose the input vector space is not linearly separable, okay? I cannot find a hyperplane, okay, to cut the two sets of classes, right? Remember week 5? Now, if we have a multi-layer perceptron, we map, we map this input vector space into a new space. Essentially, we relocate all these vectors in all these documents, right, in a hidden vector space. And because these mappings are nonlinear, we can somehow arrive at the conclusion on the right, okay? So by adding these hidden layers, I achieved something. I allowed the last hidden layer to be linearly separable, okay? So that increases the power of the neural network, okay? All right. So most of you know that, so I continue. All right. So you know MLP and neuron, the only difference is hidden layers. The more hidden layers you have, the stronger the representation power. And you know there's a theorem, right? The universal approximation theorem, which says if you have a deep neural network with more than 3 layers, you can approximate any function, okay? Any function. So that means neural networks are very powerful. But these hidden vectors are not the representation vectors we learned in this course, right? So if you take the input representation and you take one node from the input, I'd ask you, what does it mean? You can tell me what it means, right? It means there are 3 times the word go in the document, and the document is a sport document, right? You can tell me what it means. But these hidden layers, you know, you learn it directly. You don't tell me what it means, right? It's just a number. If it's just a number, then how do you have control over the neural network? This is called interpretability. I only know, okay, this is a neuron, it fires sometimes, it doesn't fire in other times, but what does it mean? So how can you make your neural network more interpretable? Okay, it's powerful, but not interpretable. So there are different ways for us to know more about the neural network. So one way is called visualization. So visualization is to say, we have a lot of instances, okay? And each instance has a representation. How do you get the representation of the instance? You feed the instance as input, right, to your neural network, right? You get a hidden layer. The instance is still represented by what we define, whatever we define. Say the word-based document vector TF-IDF, right? Okay, you feed that into your neural network, you get a hidden layer. Okay, if you calculate this for a lot of instances, we can try to visualize them. By visualizing them, I mean to turn these high-dimensional vectors into a 2-dimensional or 3-dimensional space so that you can really see them where they are. So this is one way to interpret your result, one common technique of understanding hidden layers. And there's a common visualization technique called TSNE, TSNE. The full name is T-distributed stochastic neighbor embedding. So the idea is to turn some high-dimensional vectors into a low-dimensional space by maintaining their relative distance, okay? So those vectors that are far from the high-dimensional space are still far in the 2-dimensional space, vice versa. And this picture is one TSNE visualized set of document hidden representations from a sentiment classification data set, okay? This is the last hidden layer of a neural network for sentiment classification. And as you can see, they certainly, saliently separates the positive and negative documents into two parts in a vector space. So which means, although your input documents are not so easily linearly separable, the hidden layer representation will be in a linearly separable space. Okay, so this is visualization. Now, for completeness, I must mention how to train a multi-layer perceptron. You know, when we train a multi-class classifier, we have a set of training data, right? So X is a document, C is a class label, and we have an input feature vector representation, document representation. In the new notation, it's no longer phi xi, but we just denote it as xi, bold, which means a column vector. And modeling target is still the probability of a class label given X, right? How do we parameterize this model? We can use MLP. And for sure, if we calculate probability, then the last layer is probably a softmax layer. Okay? So this is the model. The question is how to train it. Okay, to train this model, the objective function can be the same as the neuron, you know. For neuron, if it's a probability model, then what do we use? What training objective do we use? Maximum likelihood estimation, right? Okay. So the log likelihood, okay, of the data is the sum of instance log probabilities. So this is the training objective function, okay? Sum of instance probabilities. And let's suppose we use L2 regularization. So plus L2 theta square. Theta square is the sum of every parameter instance, okay? So this is a training objective function. All right, so far, everything is learned, right? Only the parameterization is different. Only that the model is something on the right, okay? The remaining are exactly the same as week 5. So given this, if you have a set of data and you have a training objective, then you have the data log likelihood, right? And then how do you train it? Of course, SGD. I don't need to repeat myself, but let's just do it quickly. You initialize all the model parameters randomly, and you go over all the training sets for t iterations, right? For each training example, you calculate the local gradient, you update your model, you move on. So that's SGD. Okay, so all in all, because our model parameterization is different, the only different thing is we need to calculate the gradients. The calculation of gradient can be different. Okay, so let's look at how we calculate the gradients for a neural network. But before I tell you something abstract, let's just roll up our sleeves and do one case, okay? So suppose that we're doing a 2-layer perceptron. And we have an input layer with 2 nodes. We have a hidden layer of 2 nodes, an output layer 1 node, okay? So the picture shows this neural network. How many parameters do we have? 6 in all. From the input layer to the hidden layer, there are 4 edges, right? And from the hidden layer to the output layer, 2 edges. Okay, so but we still have to define the activation function. So let's assume that, okay, the input to hidden activation is a square function. It's a nonlinear activation function. Okay? Why do I use a square function? Because I need you to calculate the gradient. Okay? And output is a sigmoid function. Okay? Sigmoid function, you can also calculate the gradient. And as we discussed earlier, so this, for the first y, y1, okay, the column vector, the parameter, and for y2, the parameter column vector, when we put them together, I call this matrix wy, right? And for the output layer, I call this u vector, the parameter. So wy and u are the 6 model parameters we need to calculate when we train the model. How do we get their values? We use SGD over data. For SGD, I need to calculate the gradient of the loss function, which is here. Okay? The sum of everything's log likelihood plus the theta square. Now, let us write it down, okay? Let us throw the model parameters into this conditional probability, and we got the loss function. The loss function is a cross entropy loss plus L2 regularization. Okay, so if we replace the probability with what I just told you, it will be, for one instance, okay, for one instance, xi and ci, the loss will be the log, negative log of sigmoid u1y1 plus u2y2, okay, plus lambda theta squared. What is y? Y1 is w11y x1 plus w12y x2 squared. Where does this square come from? Activation. Okay? So y2 similarly. And what is L2 regularization? You know, L2 is you minimize the sum of model parameter squared, right? So L2 regularization is translated into the last row. All right? So this is the loss function. What do we do next, folks? We need to calculate the gradient, right? We calculate the gradient and plug this into SGD and we're done, right? We can train the value of these 4 things over data. All right. Need gradient for whom? I remind you again. Wy and u, okay? So who is easier? U is easier, I think. Do we do this? The gradient of this thing over u1, okay? Okay, so you realize when I calculate the gradient for u1, we better just put y1 there. If we replace y1 into something about x, the equation will be very complicated, okay? So the gradient has 2 components. One is the gradient of the negative log likelihood. One is the gradient of the regularizer, right? For the regularizer, it's easy, right? It's just 2 times u1, right? u1 squared is there. The other parameters are not related to u1. For the gradient, for the likelihood, it's a sigmoid function, okay? I left 5 seconds for you. If you cannot catch that in 5 seconds, you take it offline. I'm taking the gradient of sigmoid of u1, y1 plus u2, y2, right? Over u1. For those of you who are quick, you will see that is equal to 1 minus O times y1. Okay? So this is the gradient of u1. You see? So if I use y1, the value of y1 here, then the gradient of the loss over u1 is simple. Okay? So similarly, the loss over u2 is symmetric. The gradients, they have y1 and y2 in them, which means, okay, before we plug these gradients into SGD, we need to do the forward computation first. We need to calculate y1 and y2 from x, because x is the input. Now the next thing is we need to calculate the gradient for wy. And here they are. Okay. They are not as straightforward as the gradients for u1 and u2, but they are not difficult either. The only thing you need is much patience, right? Because when you do the gradient chain rule, you need a square activation as well. Okay. So I don't have time to do it with you. Okay. If you're interested, you can watch my Bilibili course. It has my derivation. Okay. If you do it, it's fun. But let's just assume it's done. After it's done, I'm saying I use the matrix vector notation, okay, for the parameters. Why don't we have the matrix vector notation for the gradients as well? So if you put the gradients for u1 and gradients for u2 together, you got a gradient for the vector u, okay, which is equal to minus 1 minus oy plus 2 lambda u. It's still simple, right? It's just that I put the two scalars together into a vector. Similarly, can you put the gradient for y11, y12, y21, y22, okay? No, sorry, wy11 to wy22, okay? You put them together into a matrix, then what it is? Then you need a lot of careful reading and some intelligence. Okay, so this is what I got, okay? So it's equal to minus 2 times 1 minus O times U. And then what is this big cross? So this is called Hadamard product or bitwise product. Okay, by the name, it's just element by element, right? You multiply two vectors together. Okay, it's a product with a circle around it. Element by element product between two vectors. What is the second vector? The second vector is wy times x, okay, bracket times x transpose. Okay, so this is elegant, but not so simple, okay? So basically you're saying this is something about u, okay, and Hadamard product, or multiplied by something about wx times x. okay? And that's a matrix. That's a matrix. And then can you say, okay, we have a set of matrices as parameters, and we want to calculate the gradients of a function over these matrices and vectors. The results are matrices and vectors. Is there algebra for us to do it? In other words, can we do calculus over matrices? Who has learned that in your math class? No one. That's great, because there's no such algebra, okay? There's no such algebra. You can only do that element-wise. I try to do it, you know. It turns out that there are different ways, okay, to do matrix vector products. Hadamard product, normal product, dot product, etc. There are different ways to multiply these things together, and there are different orders. It turns out that you cannot find a fixed rule, okay? A simple set of rules to decide all these kind of parameters. So you have to do the reverse engineering. You do it element-wise, and then you see what it is, okay? This is a conclusion. But then you will exclaim, this is tedious. I only have 6 parameters. And you spend a few minutes showing us, okay, not to derive them, just showing us. So if I have a huge neural network, if I have DeepSeek, okay, I want to develop this gradients for DeepSeek. It's impossible, right? So there must be some simple ways for you to calculate the gradient. The simple idea is modularization. What do I mean by modularization? I mean a deep neural network is the stack of multiple neural layers, right? If you, okay, the developer of a neural layer can sort out the gradients within the layer, the rules to calculate gradient within your layer, then I, the neural network builder, do not have to worry about calculating the gradient for every node. I just take modules, take different layers, and I put them together. It will work. Okay? So modularize the gradient calculation. Why is that possible? Because your gradients have chain rules. Your gradients have chain rules. Okay? So, when I calculate the gradient for this neural network, when I calculate the gradient for WY11, sort of, okay, if you really did it, you will find that you do it through O to Y to WY11. This is a gradient chain rule path. So if we understand that, we say, we want to break this neural network into different components, okay? So, and then if I figure out the gradient within each component, I link them together, I calculate the gradient for every parameter, okay? So the rough process is you first do a forward computation. From the input layer to the output layer, calculate the values. And then you do a backward computation, okay? You calculate the gradient for the output layer, last hidden layer, until the input layer, okay? And I visualize that in this slide. You first do a forward calculation to find the values, and then you do a backward calculation. Okay, so how do you modularize the computation of gradients? In other words, what each layer should do. Okay? Here they are. I'm drawing each layer in this picture, you know. So each layer has an input vector, has an output vector or scalar, doesn't matter. Okay? And it has a parameter matrix W. All right. My question is, okay, no matter how many layers are after it, no matter how many layers are before it, all right, my layer must be like this. So I've defined my forward computation function, which is output vector is a activation of input and matrix. So when I calculate gradients, what do we have? Okay. Now let us assume I have the gradient of the loss function, okay, over my output vector. So this is what I know. So I don't know which layers are above me. But I assume that if they tell me the information about the gradient over my output layer, okay, then I want two things. The first thing is I want to calculate the gradient over my parameters, okay, using this gradient over my output layer nodes. And I can do that. The second thing is I want to calculate the gradient over my input nodes from gradient of my output nodes. Why do I want to calculate my input nodes? My input nodes are not my parameter. Because you need the guys below you to be able to calculate their model parameter gradients. Okay? So you need to pass this gradient over your output vector into the gradient into your input vector, who is the output vector of some other layers. Okay? So you only need these two things, okay? One is the gradient over your parameter. One is the gradient over your input vector. That's your job. So if you define these two, I can modularize the whole thing. All right. So this is what we do for our multi-layer perceptron just now, okay? Y is equal to this, O is equal to that, first equation. So loss is that, second equation. Two layers, one is Y to O, one is X to Y, okay? So for Y to O, the input is what? The gradient over O, right? The gradient over O is very simple. You can just do it in 1 second. And then, so if you know the gradient over O, then the Y to O layer need the gradient over U, which is your parameter, and the gradient over Y, which is your which is your input vector. Okay? You can calculate the two using a relatively simple way. I strongly recommend you to do it. Okay? So after you calculate these gradient vectors, you think about the previous layer from X to Y. Now, for this layer, the input is gradient over Y, okay? Which you just did it, okay? And given this gradient, okay, you need the gradient over WY. And do you need gradient over X? Not so far, because X is your document representation, okay? All right, so we do it for every layer. So I can abstract this into an algorithm, okay? This algorithm is called backpropagation because I propagate this gradient layer by layer. So the input is a neural network and a set of data, okay? you randomly initialize your parameters. And then you, for every instance, right, you do a forward computation, you do a round of back propagation, in which each layer is responsible to define their own rules. Okay, done. So after the gradient calculation, how do you finish training? Tell me one sentence. Gradients into SGD, right? And done. And then you're done, right? If you ask me to tell you what is the algorithm, I will say something extremely boring, just as what I repeated at least 6 times in week 5. You randomly initialize your parameters and blah, blah, blah. You're all tired of it, okay? And I'll stop saying it. Can I initialize my parameters to all zeros? Because for perceptron, SVM, and log linear models, you say, okay, I just initialize everything to zeros. Now for MLP, can we do that? Turns out that you cannot do that, okay? If you initialize everything to zeros, there are 2 things. The first thing is, you realize the hidden layers, they're random. You don't define them, right? So if everything is 0, everything is equal, your whole neural network will, every hidden node will have the same value. This is the first thing. They will all be the same because their initial parameters are all the same. Second thing, you won't even be able to calculate their gradients. Why? You do it yourself, okay? As a result, you need to initialize your parameters randomly. And here, there are different ways to initialize them, okay? And they were done by computer scientists over a decade ago, even longer ago, okay? These are all empirical functions. You can do your own, okay? Name it after yourself, okay? But initialization determines the final performance. In week 3, we did language models, and we learned n-gram language models. What are they? They calculate sentence probabilities by using n-gram probabilities. So n-gram probabilities are the probability of the nth word given its previous n-1 word, okay? So as I showed you here. In week 3, we take every individual n-gram probability as a model parameter, and we trained this using relative frequencies, as you still remember. Those language models can generate very interesting Shakespeare plays. Now, you know you have multi-layer perceptrons. The question is, can they be used to build n-gram language models? Okay. All right, so I just tell you the answer directly. So I want to feed the representation of the previous n-1 words as inputs to a neural network, and asked the neural network to calculate the probability of the nth word, Wn. Okay? So this is a neural parameterization of P, Wn, given W1 until Wn-1. All right. So we need to look at this neural network layer by layer. This is an MLP, first of all. Second, so if we look at the input layer, okay, it's a concatenation of word representations, right? We have n-1 word. We turn each word into a vector, we concatenate them together. How do we turn a word into a vector? Week 6, we learned that, right? You have one hot vector, vocabulary size, and you have a count-based distributional word representation, right? And you also have a PPMI representation, different representations. So you have n-1 word. So it's a vocabulary size times n-1. How do you represent concatenation of vectors? You use addition sign with a circle around it, okay? I use this to represent concatenation of vectors. Column vectors concatenated together, okay, along chopstick, okay. If you don't concatenate them into a chopstick, but if you want to juxtapose them, I use semicolon, okay? That's into a matrix. All right, so and then the second layer is H, okay? It's a single layer perceptron with tan-H activation function. We just learned this activation function. The third layer, okay, is an output layer. It's softmax activation function plus a neural layer. All right. So this is the multi-layer perceptron. For the output layer O, okay, or P, the size is the same as the number of classes for multi-class classification. And what we're doing classification over, because we're trying to predict a word, that's a word drawing game. So it's a vocabulary size class set, right? Okay, so the output vector is V size. So these are what we can observe for this neural network. So the input is n-1 times V sized. The output is V sized, okay? Both are big. Okay, so it turns out that we can use another representation, okay, to replace one hot vector or this distributional vector. We can use a low-dimensional dense vector, okay, which we call word embedding, to replace this vocabulary size word representation, okay? But how do you calculate the value of this small vector? You say if I have a vocabulary size vector, I can define what every element means, right? Now you say, I want to use a small vector, maybe only 50-dimensional or 1,000-dimensional small vector to represent every word. So how do you define what every element means? So this is the first question. Okay, so the solution is, no, you don't have to define it, okay? you treat it as a model parameter. It's just one small vector for every word. And you train it, you optimize this vector along with other neural parameters. So after you train this language model, you got this representation of every word automatically. Okay? So this is called word embedding. You say, I don't quite understand you. Okay? So how can you allocate a vector to represent every word? And then you train it using the neural network. If you don't immediately understand me, we can also visualize this. Imagine, okay, your word representation is still a one-hot vector. It's very long. One element is, okay, it's non-zero, it's 1, okay? This is a column vector. And you want to turn that into an embedding, okay, which is only 1,000 dimensional, okay? From this vector to this vector, what do you need? You need a matrix, right? You need a matrix. The matrix, how many columns are there? The same size of this one, right? How many rows are there? The same size as this one, right? So this one will be equal to this one times this one, right? Okay. So you can think about we're doing a matrix vector multiplication to get the word embedding, okay? So now you think about what is the matrix? Because your input is a one-hot vector, right? So if I turn the input horizontally, okay, there's a column which corresponds to the word which is multiplied by a non-zero value, right? The other columns are all multiplied by 0 values. So what is this column? What is this column? This column is the same as this vector, okay? So because you're multiplying with a one-hot vector, you're essentially doing a column lookup in this matrix, okay? So in other words, if I put all the word embeddings into a matrix, okay, juxtapose them together, this is the model parameter we train. And you can think about training word embedding matrix as just training another neural layer. And this layer is called a lookup layer, right? I already showed you here. Embedding of WI is equal to the lookup layer times the one-hot of WI. So now that makes it easy to understand. Of course, you can extend my picture by saying there's another layer, the lookup layer, okay? But people normally don't do it right now, nowadays. All right, so compared with traditional one-hot representation, which is a high-dimensional, manually defined, sparse, and discrete, word embeddings are dense. By dense, I mean every element is non-zero, real-valued, low-dimensional, and automatically learned, just like hidden layers, okay? They are word embeddings. And we can give the MLP a little bit change, okay? As I draw you here in this picture, I can say that for the output layer O, O is not simply equal to WOH plus BO, but I'm saying O is equal to UX plus WH plus B. Why am I adding a link, okay, directly between X and O? So people who work on neural language models find that these links give better results. They're also called shortcut connections or skip connections because you don't just do one path, right? From input to hidden to output. Now you're adding another path from input to the output, okay? So this improves the performance, and we will go back to this next week. So they give intuitively richer features for the output layer. More features for the output layer. And also for backpropagation, it can also help, which we learned last week. Next week. All right. So after we define this neural network, we can train it. The training of this neural network is just like the training of MLP we learned in the previous class this week. Okay? All right. And it turns out that this neural n-gram language model works much better than the traditional n-gram language model. So why is that so? You can tell me, well, neural networks are more powerful, so we get better results. But I tell you some very easy reason. They generalize better. Let's suppose that there are two trigrams. One is the cat run. The other is the emu run, okay? Suppose that we saw the cat run in the data set, but we don't see the emu run in the data set, okay? So as a result, the emu run is an unseen trigram. So when we do the traditional modeling, we have to use backoff or interpolation, right? We have to use bigram probability to simplify that. Now, even if we don't see emu run, we have to use the unigram run to replace that, okay? It's very inaccurate. But suppose that all the words are seen in the data set. Then you know we have the embeddings of everything, right? The neural network will be able to calculate the probability of the emu run. As long as we know the and emu. So that gives us much more flexibility. And why do you believe that the emu run will have a similar probability compared to the cat run? It's because the embedding of emu will be similar to that of cat. Really? That amazing? Okay, I will show you later, okay? But so far, you learned that, you know, the word embedding is a byproduct of training a neural network, right? When you train the n-gram language model, you got a set of embedding. Okay. And then researchers began to think, okay, I'm telling you, this neural model, okay, the neural language model I told you was invented in 2003, okay? Oh, that's long in history. And then in 2013, okay, that's long in history, not long in history. People begin to realize the importance of word embeddings. And some researchers, they stand out and say, okay, can we train an n-gram language model over the whole internet so that we get embeddings for every word, okay? So that's the question people raised in 2013. At that time, GPU is not that popular yet, okay? So people have to train the whole neural network over CPU. And if you train it over the whole internet, it will take a long time. So you have to simplify the neural network in order to train word embeddings faster. Okay? How do we simplify the neural language models we learned? There are two directions. One is to simplify the training speed. One is to simplify the model itself. And different people develop different methods to that end. And I'll share with you one method for training, two methods for model simplification. The model for training is named noise contrastive estimation. Okay, so I will tell you why it's called this name later. But first, let's look at the training objective again. All right, it's just a negative log likelihood, okay? And we can calculate the gradient of this loss over every training instance, as I show you here. And you've seen that at least 3 times in my class. One time for log linear model, second time for CRF, the third time here. Okay? But they are different only in parameterization. The shape is the same. So the gradient will be equal to the last hidden layer representation minus the expectation over all possible word, the last hidden representation. All right? So, but there are two things that are slow. The first slow thing is this O vector is very long. If you calculate for every bit, it means that you have to calculate for every vocabulary word. It takes a lot of time. The second is the summation here is very big because you need to sum over the whole vocabulary. Okay? Okay, but the two problems is a single problem. The two problems are the single problem. Because if you can enumerate every word in the vocabulary and you sum them up, you also get this O. So basically, it's the vocabulary stuff. But we worry about the summation here, and we worry about the calculation of O in the simplification of neural network structure. Can we simplify the summation? So noise contrastive estimation proposes a different training objective function, okay? And optimizing this training objective function approximates the optimization of the cross-entropy loss. So what is this new objective function? It is noise contrastive estimation. So first of all, what is contrastive estimation? Contrastive estimation trains a model, okay, by contrasting some samples with other samples. What do we contrast? We contrast samples in the data with samples not in the data. Okay? What do we call samples not in the data? Noise. Okay? So that explains the name. So for things in the data, okay, we use D, data, equals to 1 to represent it. It's a random variable. For things not in the data, we have D equals 0. So if we saw the cat ran in the data, then D equals 1 for that. If we don't see the cat dog, the cat blue, and the cat fast, those trigrams are not in the data, D equals 0. Second, okay, it's easy to get those trigrams in data, but how do we get trigrams not in data? We need to sample them, okay? We learned okay, basically how to sample by throwing a dice, right? And we learned how to sample a sentence in week 3. Now, what we do is we can sample trigrams, okay, by given a context, which means the previous 2 words, to sample a third word, okay? Now, we can sample this third word according to uniform distributions, okay? Or we can sample according to empirical distributions, which means we first train, basically, bigram language model, trigram language model, and we sample. No matter what, okay? Suppose we have the sample distribution Q, maybe a uniform, every word is equal. And we have the empirical distribution, which is P, relative frequency. We can calculate one thing. So given the context, given the cat, okay? So what is the probability of a real word D is equal to 1, a sampled word D equal to 0, okay? And that is equal to, given C, we first decide whether we sample or not, PD. And then we decide PW given DC, which is either P or Q, right? So this is the equation. So what is PD? It depends. It depends on how many negative samples we want, given every positive sample, okay? So this PD will basically be the proportion. So let's say for every positive sample, let's sample K negative samples, okay? So PD equal to 1 will be 1 over K, right? So this is predetermined. So given this, we can calculate, okay, the probability of D given C and W. Now this is the modeling target. What do I mean by probability D given C and W? We only know straightforwardly PD W given C, right? Now PD given C and W means if I just throw you a trigram, the cat blue, how likely it is this is generated? How likely it is? This is from data, okay, the cat blue. So if your model can differentiate these cases, then your model can generate trigrams, okay? So the NCE, contrastive estimation, modeling target is D given C and W. And that can be estimated using P dW given C. How do I do that? I show you in the equation here, okay? It's just conditional probability. PD given CW is equal to PDW given C over PWC. PWC is the marginal probability of PDW given C. So PD given CW is equal to PDWC given C divided by the sum of both D0, D1, okay, PDW given C, okay. And PDW given C is already known in the previous slide, so we can define these equations here. But these equations all have P tilde here, right? So it's a relative frequency. We don't want relative frequency. We're only able to train our model using these equations. So we need to replace this empirical distribution with the model distribution, which is here, okay. So it's a softmax over O. Okay. So if we replace that and we put that into the contrastive objective, we realize, okay, there is still an exponential sum, which is Z, okay? We still have to train exponential sum. So we need to simplify this a little bit. The simplification, again, is to assume that Z is equal to 1. So the model probability is just simplified into the e to the power of O, okay, W. Now, some amazing things happens. If you don't have Z, you realize, okay, you only need OW, right? OW is just one bit in the output vector, okay? Which means you don't have to calculate every bit, the whole vocabulary probability. You only need to calculate the score of one word, okay? Okay, not one word, but K plus one word. To finish this contrastive estimation objective function. So let me repeat myself. So given a trigram in data, the cat ran, okay? You first sample K fake stuff, the cat blue, the cat dog, etc. Okay? And then you use these two equations to calculate whether these K plus 1 trigrams are from data or not, using these equations, right? And in this process, you involve the model by calculating O of W, just one bit in the output. So no exponential sum, no exponential vector calculation. Okay, so this is how we calculate the probability of D, okay, using my training instance, the trigram. But what is the training objective? It's here, okay? We still do maximum likelihood. We still do it. But this time, the likelihood is calculated over PD, not the probability of trigram anymore, okay? And that's easy to compute. And you say, oh, why do you take all this long way just arrive at this simple calculation? It's because I showed you in my textbook, I proved it. When K tends to infinity, which means if your negative samples cover, okay, infinite number of possible words, or if you sample over the whole vocabulary, maximizing this thing, not simply sampling over the whole vocabulary, okay, sampling over infinite number of samples. Maximize this thing is exactly the same as maximizing the original log likelihood. Okay? So we are there. So we found a new problem, right? Guess, am I real? Okay? And I maximize the likelihood of this problem. We can indirectly maximize the likelihood of the original problem. This is NCE. I showed you there are two other things to simplify the neural network. Okay, these two things are very easy to understand. Okay? The first is called hierarchical softmax. And this thing is still used in some recent work, okay, to simplify, to make LLMs smaller. So the idea is the mapping, okay, you know your neural model, right? It maps from X to H to V, right? So if H is big, this H to V matrix will be the H size times the V size, which will be a big matrix, a lot of computation. So can we make it smaller? The basic idea is to break this H to V mapping into a H to M mapping and an M to V mapping by introducing a very small vector M, okay? So this M can be intuitively understood as, okay, I introduce a few semantic categories over the vocabulary, and I attribute the vocabulary into these categories, okay? So I first predict these small attribute categories, M, using my H, and then I generate the whole vocabulary distribution according to my M, okay? So why does it simplify calculation? Because I show you in this last equation, right? So by introducing M, your new matrices can be much smaller. Another way, more drastically simplifies the neural network, is to remove H at all. Okay? So how do you do that? It's done by using embeddings to represent words. But you need two sets of embeddings. So one is how to represent, okay, the input. One is how to represent the output, okay? Now suppose that the input, C, which is, okay, the context, the cat, for example, is every word in C is represented by a set of embedding, okay? So I can simplify, do a weighted sum of these embeddings. So I add up the embeddings of the and the embedding of cat, okay? Maybe we can have different weights to different previous words. The closer word have higher weights or equal weights to every word, okay? So I add the embeddings together, and then I got the output embedding, maybe run, okay, the embedding of run. So I just use the sum of embeddings of the cat to dot product the embedding of run, okay? And that's the similarity score. Or I can use different similarity scores, but I just do this simple calculation. You can save the hidden layer. This is called log bilinear model. Why is it bilinear model? Because the probabilities are the product of two linear representations. Okay. With these three techniques, I'm able to tell you some algorithms to calculate word embeddings over the whole internet. Okay? So the idea is told. So we simplify the n-gram language model. And I use the simplified language model as the training objective over a lot of data, only to get word embeddings. I'll discuss three word embedding algorithms. The first one is called continuous bag of words, or CBO. Okay, so this CBO algorithm has a slight setting change over the n-gram language model. Rather than predicting the next word, given the previous word, I predict the middle word, given the surrounding words. Okay? As I draw in this picture. As a result, it's not an n-gram anymore. It's a skip-gram. I skip a word, and I predict this word. Okay? And okay, so this is the modeling target. The probability of the skipped word given the surrounding context. What's the modeling technique? What is the parameterization technique? The parameterization is just a log bilinear model with NCE training. Let me show you. Okay. On the right is this model. I have surrounding words on the left. I want to predict the probabilities of the skipped word on the right. And I call the skipped surrounding words, okay, W1, WI1, WI2 until WI2C, okay? It doesn't matter how you index them. And I give them a set of embeddings, okay? I embed them all together. And I just add these embeddings together, okay? And divide it by 2C. So I calculate the average. So this is one representation of the context. I call it H. So for every possible output word in the vocabulary, I calculate a set of embedding as well. But now I use a different embedding table, okay, to calculate the embedding of output words. So I name it embedding prime. All right. And the probability is just represented by the dot product of the two embeddings, okay, and the softmax activation. So this is the parameterization. How do I train it? Okay, I don't want to train it over the whole vocabulary. So I just don't use the original softmax setting, but I turn this into a guess who I am game, right? So you're given a trigram, you sample k fake trigrams, and you use the probability of D, okay, to represent guess who I am, and you maximize the likelihood of PD. This is NCE. With that, you can train the embedding and embedding prime values over the whole internet, okay, very fast. And it turns out that these embeddings work very well. How do you know they work well? I'll tell you later. The second method is called skipgram, okay? Skipgram is a slight change of continuous back-of-word model. You don't predict the skipped word, okay, using the surrounding word, but you use the skipped word. To predict each surrounding word individually. The idea is to make sure that in a surrounding window, every word embedding is close to everyone else. Okay? So this is a very simple idea. And the model parameterization is also very simple. There is no summation anymore, right? But there are more dot products because you want to use the skipped word to predict every surrounding word. Okay. And this is also trained using NCE, so I will not repeat myself. Okay. So there are two slight variations of the same thinking, and they both work nicely. There's a third algorithm, which is slightly different from the first two. But no matter whether they are the first two or the third, they're all called distributed word representations. Okay. Of course, why are they distributed representations? Because they're calculated over a whole data distribution. All right? And why do we call it distributed? Because the word distributional was already taken. Okay? We introduced in week 6. So CBOW and skipgram, they calculate distributed embeddings, okay, by going through the internet, training the model over one n-gram after another. So this is called online learning, okay? GLOVE is a way to train word representations using global statistics directly, not online learning. So why don't we just first calculate the distribution? And we do that by defining a huge matrix, X. This X is V by V size, okay? So every element in X contains the count of co-occurrence between two words, okay, in a window over a large corpus. Okay? So this is called a co-occurrence matrix. So if cat and ran co-occur 10,000 times over the internet, maybe much more than that, okay? So I will have 10,000 in the cell between cat and ran, okay? What do I mean by co-occur? You can define the window size. If the two words are in this window, they co-occur. Now, X is the global statistics. I want to train embeddings to make sure that these embeddings follow global statistics. How do I do that? Okay, this is the training objective. I want to make sure that the dot product between two words, okay, is proportional to the log of the co-occurrence value. Simple, right? And you can think about that as glove. But wait, you ask, what are these BI and BJ? Okay, these are bias terms, okay? To avoid some effects of frequent words, like co-occurring a lot with other words. So the loss function is like this. It's a mean squared error loss, which you see in machine learning problems elsewhere, okay? I just want to make sure that these dot products, they are similar to the logarithm of their co-occurrences. Given a weight, again, this weighing function is an engineering trick, okay? To avoid bias. If you're interested in the mechanism, you can read the textbook. We have one last topic, which is how do you evaluate word embeddings, okay? So a direct way to evaluate word embedding is called external evaluation. So from next week onwards, we will see a lot of neural models who take word embeddings as inputs. So if one set of embedding gives stronger results on NLP tasks, then they are better by external evaluation metric. But you can also evaluate word embeddings internally by their linguistic characteristics. And to that end, I just quickly introduce two tasks. One is called word similarity. One is called analogy, word analogy. Word similarities are like this. Given any two words, I can ask a human student to give their similarity score between 1 and 5, okay? And if you're trained properly, you can be able to give the similarity score. Okay, also maybe between 1 and 10 or 0 and 1, doesn't matter. I can have human to score the similarity between a set of words. And we can have word embedding similarities by using their dot product, okay? And when we have this human labeled set of words, I can calculate, okay, how well does the word embedding similarity correlate with the human similarity? And to that end, we have some correlation scores. And one is called Pearson correlation, okay? I don't have time to go into the details of Pearson correlation calculation, but it's easy to understand. You can read it offline. It turns out that this set of word embeddings correlate quite well with human ratings. The second task is called word analogy. And this is, again, an interesting task. It's a similarity between word pairs, okay? For example, Beijing to China is similar to Bangkok to Thailand, or Seoul to Korea, okay? And I can give you a few other examples, and you can guess, right? The correlation between two words are similar to the correlation between another two words. Okay, this is called analogy. So I can give you different questions on analogy. For example, one question is, given that a word pair is king and queen, okay, and the third word is boy, what do you feel to the fourth word, okay? How do we evaluate word vectors? We can just find, okay, the vector space correlation between word vectors to identify analogy. And it turns out that skipgram works very well to that end. Finally, this is a visualization of word similarity and analogy using t-SNE, okay? Here in this example, you can see that the geometric relation, I shouldn't say geometric relation because it's already visualized in 2 dimensions, okay? But the algebraic relation between man and woman is very similar to that between king and queen. All right, for today, I just did 2 things. One is to go over MLP and deep neural network for text classification. Second is I introduced neural n-gram language models and word embeddings. Right? Next week, we will move on to neural NLP.